For Lab 6, I implemented the wave function collapse algorithm. The name of this algorithm is derived from a quantum mechanics uh, principle where a wave will collapse once being observed into one of several eigenstates when previously it was a superposition of eigenstates, or in other words, it was all of the states all at once. For the sake of this lab and this algorithm, it doesn't have to do with quantum mechanics per se, but rather it's used as an analogy for procedural generation. The implementation of this was done first by creating a grid. This grid is specified with rows and columns, and each um, cell within this grid has a set of constraints as well as a set of neighbors. The constraints is a list of states. Each state, as you'll see in the next slide, has certain rules that they have to follow. The neighbors within each cell corresponds to the north neighbor, south neighbor, east neighbor, and west neighbor. And again, the algorithm checks if each neighbor is allowed to be to any of its other neighbors. For the implementation, what I've done is, for right now, I've done what I've called one-dimensional state constraint. What this essentially means is that each tile in this sort of palette that you can see can only be next to a maximum of 2 other tiles. For the sake of this implementation, what this looks like is as follows. The deep ocean can only be next to the water. Water can only be next to deep ocean and ocean. And ocean can only be next to water and sand, and such and so forth. Now, the direction doesn't actually matter. It's just depending on what is next to what. What this looks like in practice then is, I have 2 examples here. What you'll notice is sometimes the tiles will collapse almost as if it's following out a branch, but then sometimes it will follow from bottom to top. The reason for this is when it is iterating through each cell in the matrix, rather than pick at random, which is what I will work on implementing next, it is just picking what is considered the lowest entropy, which is this algorithm's heuristic. Lowest entropy in that sense just means what is the least amount of possible states, or the smallest superposition at the time. So the next steps of this is optimization. Like I mentioned earlier, the algorithm iterates through the entire matrix. The problem with this is that not every cell in the matrix needs to be iterated through. If you look over here, a lot of the cells are going to actually stay white for some time. So there's no need to necessarily have them. In fact, all we really need is maybe 2 away from the last given cell, or 2 away from the edge sort of creeping in. Implementing that would be something that would allow for much faster code. Right now, I'm sort of constrained to grids of 20 by 20. Anything over that takes a little bit too long. For example, if I had 100 by 100, that's over 10,000 cells to iterate through. On top of that, each cell needs to be iterated about 7 times per superposition, leaving me about 70,000 loops per frame update. Obviously, that's pretty computationally expensive and does not need to be done every single frame, like I said earlier. I'd also start implementing using 3D prefabs rather than the traditional single pixel tile like you can see here. This will allow for just a more interesting outcome, but because they're prefabs, shouldn't necessarily be a huge impact on the performance. Lastly, I'd like to implement 2-dimensional state constraints. Like I said earlier, this is only one-dimensional. It can only have two neighbors at any given time, whereas a two-dimensional would probably have four neighbors, as it can be, neighbors top, bottom, left, and right. And then maybe if I can complete that, three-dimensional would be interesting. However, the problem with this is it would have a big impact on the performance. So unless the initial optimization that I have planned can be done, I would most likely just be sticking to one-dimensional state constraints.